Welcome to 3.2, Part 3, where we delve into the first theorem, the remainder theorem. Go ahead and pause the screen so you can write the remainder theorem down, and we will go through exactly what this means through some examples, but basically it's telling us about the remainder, and it says that if we divide some polynomial, p of x, by x minus c, and we can use synthetic division with c in the corner, then the remainder is the same thing as if we were to just evaluate the function at c. Let's take a look at a few examples. Example 1, we want to determine p of c, where c is 3, so p of 3, using the remainder theorem for this cubic trinomial here, p of x. So our remainder theorem tells us that instead of just finding p of 3 by direct substitution, we can do it even more quickly by finding the remainder when we divide p of x by x minus 3. So doing that means doing synthetic division, where we put 3 in the corner here, and then we're essentially, remember, we're dividing p of x, our function, and we're dividing it by x minus 3. That's the same thing as saying c is 3 right here. That's what we're doing. So I'm going to see if I have any skips here, any missing terms. I have a cubic term, a quadratic term. I don't have the linear term, and then I do have a constant. So we will need one 0 placeholder, so we'll have a 5, a -2, a 0, and a 1 there. Then we're going to do our synthetic division, so we bring our first number down. Then we multiply 5 times 3, and we put that here. Then we combine or add vertically here, so we'll put a 13 down here. Then we repeat our process. 13 times 3 is 39. Then 0 and 39 added together is 39. 39 times 3, let's see, 40 times 3 is 120, and then we'll take away 3, so 117. And then we add those together and we'll get 118. That again is our remainder. So the remainder theorem tells us that our remainder, 118, is p of 3. So our remainder theorem tells us that p of 3 is 118. It's what we'd get as the remainder if we divided by x minus 3, meaning do synthetic division with 3 in the corner here. Now, can we double check our work? Sure. You can totally use a calculator or you can do it by hand. So to check our work here, we can check by doing substitution, and we can actually find p of 3 to make sure that it is in fact 118 by just directly plugging it in. So I'm going to plug 3 into our function and see that we do in fact get 118. So we'll have 5 times 27 minus 2 times 9 plus 1. And that is 135 minus 18 plus 1, which is 118. So we checked our work by using, by evaluating our function or using substitution, however you'd like to say it. So we use the remainder theorem, which again tells us the remainder is what that function is evaluated at our c value. And then we can check our work using ideas that we already know how to do by evaluating the function at that point. Now, something that we do know here is that x equals 3 is not a 0, is not a root or x-intercept of p of x. It didn't give us a 0 out. So x minus 3 is not a factor of this polynomial. It does not fit in perfectly. There is a remainder there. And also the coordinate point 3, 118, which is crazy far away from the x-axis, is on this function, meaning it's not an x-intercept, obviously, because it's not hitting at the x-axis. So 3 is not a root, 0, or x-intercept, whatever vocab word you'd like to use. 3 is not a 0 of p of x. Okay, let's take a look at another example. Okay, example 2 is written slightly differently, but it's the same idea. We're given again, a cubic trinomial, and we want to find p of -2 using the remainder theorem. Again, I know that you know how to find p of -2 by direct substitution and plugging it in, but we want to use the remainder theorem, which tells us that when we take p of x and divide it by x plus 2, right? Because in this case, c is -2. That's just another way. This is another way of saying c is -2. So it's testing the x value of -2, meaning this would be our factor. So this is another way of saying p of x divided by x plus 2. And whatever our remainder is, that's the same thing as plugging in -2 to p, finding p of -2. So let's do that using synthetic division. So we're going to put -2 into the corner. And I just wrote p of x here instead of writing it all out, but it's up here. So we're skipping the quadratic term here, so we do have to put a 0 placeholder in for that. 2, 0, -5, and 3. And we'll perform our synthetic division. 2 times -2 is -4, combining vertically. Then multiplying again, -4 times -2 is 8, combining vertically. 3 times -2 is -6. And then our remainder ends up being -3. So what the remainder theorem tells us, so thus, or in conclusion, those cool 3 little dots, p of -2 is -3. That's what it tells us, which is pretty cool. Let's check our work using substitution. So let's check using a method that we already know is true, substitution, or evaluating the function at -2. So finding p of -2, we're going to plug in -2 everywhere that there's an x. Just a quick reminder, when you are cubing a negative number, you do get a negative out. So this is going to be 2 times -8. This will be a plus 10 and plus 3. Over here we'll have -16 plus 13. And that does, in fact, give us -3. So, like in our first example, -2 is not a 0, aka a root, aka an x-intercept, of p of x. The coordinate point -2, -3 is on this function. Therefore, it doesn't hit the x-axis. It's not a 0. Also, it doesn't literally pop out a 0. So, this is the most we're going to do here. It also means that x plus 2 is not a factor of p of x. It doesn't fit in evenly. There's some extra here, a remainder. In example 3, we're going to stick with the p of x from the previous example, and 1 is actually a root. So let's go through the remainder theorem here again. So finding p of 1, remember that means this is just another way of letting c be 1. And essentially, we want to take p of x and divide it by the factor x minus 1. Remember, this is always the factor x minus c. This is saying c equaling 1. C is just a specific x value we're talking about. Okay, so what we want to do, what the remainder theorem tells us, is that if we divide p of x by this factor here, using synthetic division with 1 in the corner, whatever remainder we get out is p of 1. So again, we're going to set up our synthetic division in the same way, put a placeholder for the quadratic term, and perform our synthetic division. 2 times 1 is 2. Combine 0 and 2 to get 2. 2 times 1 again is 2. Combine -5 and 2 to get -3. -3 times 1 is -3, and combine actually to get 0 here. So our remainder is actually 0. So in conclusion, using the remainder theorem, we have found that p of 1 is 0. Now, zeros are important in math if you haven't picked that up yet. This means that the coordinate point 1, 0 is on our graph. So I just drew this real quick. That's that coordinate point, 1, 0. I do know other things about this graph. I could find the end behavior. We could go on and on about this. I don't really care about that right now. But what I do care about is understanding the importance of getting a 0 out. That means that we literally are hitting the x-axis. 1, the x-coordinate of 1, is a 0 or a root, or an x-intercept, however you'd like to say it, again, of p of x. So this is an important number. It means that x minus 1 is a factor of p of x. When we divided by x minus 1, it fit in perfectly. There was no extra, no remainder. So another thing that we can do is we can rewrite p of x looking nice here. So here's how we can rewrite p of x. I didn't actually double check this by using substitution, but that's okay. We'll trust that we did it right here. Okay, so we can rewrite p of x like this. We can say that p of x, our original function, is partly x minus 1. That's one of the factors. That's our divisor. And then we can multiply it by our quotient that we got here. This quotient is a quadratic because we started with a cubic. So this is a quadratic. So it's 2x squared plus 2x minus 3. And that's how we can rewrite p of x. We don't have a remainder. We don't really care too much about rewriting functions if there is a remainder here. We don't really ever see that in factored form. This is the factored form of p of x. X minus 1 is a factor of p of x. It fits in evenly. Think about factors of numbers, right? Like factors of 10 are 1, 2, 5, and 10. They fit in perfectly inside 10, no remainder. That's what it means to be a factor, is that you don't have a remainder, or your remainder is 0. So some things that we know x minus 1 is a factor of p of x. And we also know x equals 1 is a 0 of p of x. Now, how many zeros are there? Well, this is a cubic, so there could be at most 3 total. This is easy to see. We set this equal to 0, we get 1. We already know how to do that. This one we could maybe factor, we could use the quadratic formula. We will eventually get there, but there's potential 2 more zeros found in this extra quadratic that we found. Okay, this last thing that we're going to talk about quickly is just the relationship between zeros and their corresponding factors. So if x equals c is a 0 of some polynomial, then x minus c is a factor. So for example, if x equals 2 is a 0 of our polynomial, and that looks like a z, not a 2. Let's make it look like a 2. If x equals 2 is a 0, then x minus 2 is a factor. We'll do one more. If x equals negative 8 is a 0, then x minus negative 8, or x plus 8, is a factor. During all these examples, we just called this value here c, and then if it's a specific value, we see that it's like the opposite in its factor. All right, that was our hopefully quick video about the remainder theorem.